Selamat sejahtera. We are from Group F, Section 2 from Solid Mechanic Laboratory, BDA 17301. Now we'll present about the lab experiment presentation of the title Tin Cylinder. So these are our group members: NAJMI, NAZMI, AMAR, SYAFIQ, and me, Yong.
Assalamualaikum. I'm NAZMI, so I will present about the theory of the tin cylinder. So, the tin cylinder experiment is used to investigate the stress in a tin wall cylinder. A steady steel frame supports a cylinder with a tin wall made of aluminium alloy. Internal pressure is applied to the cylinder by a hydraulic hand pump. So, a pressure gauge indicates the cylinder's pressure. A hand screw is attached to one end of the frame, which operates as a piston on one side of the cylinder. Applying the hand screw causes either circumferential or axial tension on the cylinder. The strain gauge mount to the cylinder at various angles. Each strain gauge is hooked into the complex bridge temperature correction and zero adjustment in the bridge box with the strain gauge indication. So the tin cylinder also described as a cylinder having a substantially larger diameter than their wall thickness. In other words, a tin mechanical cylinder or vessel is a cylinder with a wall thickness less than 1/20th or that of its internal diameter. So radial thrust is considered minimal in mechanical calculation that use a small cylinder. A tin pressure vessel is closed, cylindrical or spherical container that is intended to keep or store fluid at a pressure significantly higher than the ambition pressure.
Hello, my name is NAJMI. For the observations, during laboratory-based experimental research, a comprehensive observation was conducted on tin cylinder subjected to varying external pressures. It was observed that increasing the external pressures led to a clear and steady rise in the cylinder's radial displacement, indicating a direct correlation between external pressure and deformation. This phenomenon underscores the material's susceptibility to mechanical stresses and highlights the complex interaction between external forces and structural response. Additionally, the experiment demonstrates an increase in horizontal displacement with higher external pressures, providing crucial insight into the material's mechanical behavior under different conditions. This detailed analysis enhances our understanding of the mechanical properties of tin cylinders and carries significant implications for applications involving deformable structures. Through meticulous documentation and analysis, scientists can gain empirical insight into the intricate dynamics controlling tin cylinder behavior under external pressure, thereby advancing both theoretical models and engineering solutions aimed at optimizing material durability and performance under similar stresses. This observational approach not only facilitates innovative approach to tackle challenges across various fields, but also reinforce the empirical foundation of material science and engineering methodologies.
Now I'll be presenting the results of our first experiment involving a tin cylinder with open ends under different pressures. We measure the response of 5 different gauges to pressures ranging from 0.5 to 3 megapascal. As we can observe from the table, the readings for each gauge increase consistently with the applied pressure. For instance, at 0.5 megapascal pressure, the gauge read from 1 to 5. As we increase the pressure to 3 megapascal, the readings proportionally escalate to values between 4 and 44. This clear pattern demonstrates a direct relationship between pressure and gauge response, which supports our initial hypothesis regarding the behavior of the tin cylinder under pressure. For the closed-end experiment, we measured the pressure at a consistent value of 3 megapascal. The readings across the 5 gauge reveal a progressive increase in pressure, starting from 6 megapascal at gauge 1 and increase to 47 megapascal at gauge 5. These results demonstrate a clear relationship between gauge number and pressure readings. In the calculations for hoop strain and longitudinal strain for thin cylinders with open ends, we utilize the specific formulas and the given technical information. The wall thickness is 2.5 mm. Young modulus is 70,000 Newton per millimeter square. Radius is 36.25 mm and the Poisson's ratio is 0.33. For example, a pressure of 0.5 megapascal. We calculated the hoop stress as 7.25 megapascal by using the formula stress equal to PR over T. The hoop strength was determined to be approximately 1.0357 times 10 to the power negative 4, while the longitudinal strain was found to be negative 3.418 times 10 to the power negative 5. These calculations demonstrates the deformation characteristics of the thin cylinder under the specific pressure conditions. As we can see in the result, the calculated hoop stress increased proportionally with pressure starting from 7.25 megapascal at 0.5 megapascal pressure to 43.5 megapascal at 3.0 megapascal pressure. Hoop strain remained constant at zero across all pressure levels due to the open ends. The longitudinal stress and strain values, however, show significant variations. Longitudinal stress increased from negative 3.418 times 10 to the power negative 5 megapascal at 0.5 megapascal pressure to negative 2.051 times 10 to the power negative 4 megapascal at 3.0 megapascal pressure. Correspondingly, longitudinal strain increased from 1.0357 times 10 to the power negative 4 at 0.5 megapascal pressure to 6.214 times 10 to the power negative 4 at 3.0 megapascal pressure. These findings indicate the impact of increasing pressure on the deformation and stress distribution within the cylinder. In the second experiment, we focus on calculating the hoop and longitudinal strains for a thin cylinder with closed ends under varying pressure conditions. Using the same technical specifications, the wall thickness of 2.5 mm, Young's modulus of 70,000 Newton per millimeter square, radius of 36.25 mm, and Poisson's ratio of 0.33. We calculated the strains for a pressure of 3.0 megapascal. The hoop stress was determined to be 43.5 megapascal, while the longitudinal stress was 21.75 megapascal. The resulting hoop strain was 5.189 times 10 to the power negative 4 and the longitudinal strain was 1.056 times 10 to the power negative 4. These values reflect the significant impact of closed-end conditions on both hoop and longitudinal strains, highlighting the cylinder's deformation characteristics under pressure.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AMAR bin Muhammad ZUKI. My method number is DD230080. Now I will present and share about discussion. And discussion divided into two questions. I will share both of questions. So the first question is asked, explain the difference between open ends and closed end condition. Okay, we can see five type of different that we can find. First, setup. Second, piston position. Third, force transmission. Fourth, stress result. And for the fifth, strain formula. Okay, for the open ends, setup, fully screw in the wheel, and close end is turn the wheel to the maximum. Piston position, no space or contact between piston and cylinder end cap. Piston can move outward against cylinder end caps. Force transmission, axial force goes directly to the frame via pressure oil. For closed end, axial force transmit into the cylinder from pressure oil. Stress result, longitudinal stress equal to zero. For closed end, stress result presence of axial and longitudinal stress. Hope stress is also present. Both hope hope strings and longitudinal strings formula are different for open ends and closed end. That's all for question A. Okay, now we proceed to question B. The question asks which cases experience uniaxial stress and biaxial stress. Okay, for the answer, open end cylinder is uniaxial stress. The reason why, first, internal pressure distributed outwards from the center perpendicular to the axis the cylinder axis. The second one, no end constraints or length restriction. The third one, no axial forces leading to no longitudinal stress. And the last one is deformation or expansion occur freely. And for biaxial stress is refer to closed end cylinder. The reason why, first, internal pressure affect both radial and axial direction. Second one is end constraints present, and the last one is axial stress is considered, resulting in both hope and longitudinal stresses. That's all for discussion. Thank you.
My name is Muhammad Shafiq bin Samsul, and now I will present conclusions. For the conclusion, measure stress and strain in a thin wall cylinder under internal pressure. Modify axial stress in the cylinder wall by comparing experimental findings to theoretical computation. Computes Young modulus, Poisson ratio, and hoop stress using 6-strains gauge. Impact the cylinder wall by using both closed and open ends. Accurately measure strain in the thin cylinder wall under varying interior pressure. Issues include accurate alignment and attachment of strain gauge and sealing of cylinder ends. Enhance experiment by performing multiple trials at pitch, pressure, and using more accurate pressure measuring tool. Offers insight for safe vessel design and verification of engineering practice analysis techniques. That's all from me. Thank you.
These are the references that we use to complete our report.